Welcome to Learn Python, and in this video we're going to make a model that's going to be able to take one of these images and actually produce an output. So in our last video we went and downloaded a data set and some data loaders. And in this video we'll make a model that's actually going to be able to take in these images and produce an output. So without further ado, let's get right into it. First thing we need to do is make some imports. So from torch import nn. So nn is the submodule that all neural networks in PyTorch use. So we're going to need that, and that's about it. So to create our model, we need to create a class. That's what PyTorch likes. So we'll do class, call it net, and then two parentheses, nn.module. This essentially tells PyTorch, hey, this class is going to be a neural network. Let's add our def.init, definite. We'll do self, and I'll add one parameter called fc input. For now, I'll set that to like 1. I'll tell you guys why later. Next, let's do super.init. Good. And then after that, we'll actually set up our convolutional neural network. Now, I'm not going to explain what it is fully. You guys can search that up. But essentially what a convolutional neural network is, it's a type of neural network that's really good at computer vision. So let's start making that. We'll do self.conv1. This is going to be our first convolutional block. Set to nn.sequential. And then we're going to need our first convolutional layer. We're going to do nn.convolutional 2D. Why is it 2D? Because the data is 2D, you see? We have an image here, the x, y, that's 2D. If we were giving our model maybe a video or a 3D model, then we'd be using 3D, but in this case, just 2D is fine. Next, we need to set our in channel. So as you can see, when we went and made our transform, we set our grayscale to return 3 output channels. Let me just show that. We can go to our train data set. Let's do train underscore data set, access the first image, and then do dot shape. As you can see, this number right here is the amount of channels, and these other numbers are dimensions of the image. So we have 3 input channels. Next, we can expand that to, using out channels, we can expand that to, I think 32 would be a good number. And then we need to set our kernel size. So what a kernel is essentially, it's sort of a square that slides over this image and sort of extracts patterns from our image. And that's sort of the core of a convolutional neural network. So let's go ahead and make another layer, conv2D, in channels. And this needs to match with our ouch channels over here, equals 32. And then keep your kernel size of 3.3. If you're wondering why it's 3.3, it's because it's more optimal for it to be 3,3. You know, we just figured that out over years of research. So now we have, hold on, I forgot to set an out channels, sorry. Out channels is equal to 16. Okay, now we have our first 2 convolutional layers. Now I'm gonna add some extra stuff. Next thing I'm gonna add is an nn.maxPool2D. And then set a kernel size is equal to 2, 2. Now what this does is it takes a kernel of 2 by 2 pixels, it slides across your image, and what it does, it takes a 2 by 2 layer and turns it into a 1 pixel. And what that does is it effectively reduces image by half in terms of size. And what this does is essentially it improves computational performance while not losing too much, accuracy in the model. So it's a great way to, if you don't have a GPU, then it's a great thing to use. Lastly, we added nn.relu. And this is just a rectified linear unit, so all it does is it takes negative values and sets them to 0. And what that does is it just makes the model just better at predicting non-linear things. Okay, that's our first block. Let's go ahead and copy this to create a second one. I think 2 is all we'll need. Self.conv2. And then our in channels, we need to match with the out channels here. So we'll set to 16, and this is where I like to scale down. So we'll do 8, keep it at 8 here, and then 4. 4 will be the last. Great. Okay, let's delete that. Now we have our 2 convolutional blocks. And at the end of this, when we pass our image through this, we'll still have an image left. It'll be smaller, a little distorted because of all the sliding, the kernels. But after all that's done, it's still an image. We need a way to give it to a multi-layer perceptron, and that's actually going to be able to produce an output. So we're going to create something called a self.fc. FC stands for fully connected layer. nn.sequential. And the first thing we need to do, this is very important, nn.flatten. What this does, it takes sort of an image tensor into like a flat list, sort of, you know. So before we had, like a shape of 223 by 224 by 224, instead of an image, what it'll do is it'll just create it into just a one length like this. I don't know if that's the exact number, I don't know, but that's sort of the overall idea. Now the problem is we actually don't know what the size of this flattened tensor is going to be, and that's why I have FC input. So we can do nn.linear in features, not features, not channels, and then we're going to set that to FC input. Next we'll do out features. This should be pretty customary. 512. Do nn.linear again. In features is equal to 512. Out features, let's do 216. 64 actually. And then lastly, do nn.linear. In features is equal to 64, and then out features. Now this is where I want my input. So as you can see, 0 and 1, I want the model's prediction to be between 0 or 1. So if it produces 1, then it thinks that this image has pneumonia. If it produces 0, then it thinks this image does not. So we'll do out features equal to 1. That means it's going to be a returned is a number between 0 and 1. Okay, let me just maybe see an image. Oh, got a comma there. There we go. That's pretty much the structure of the entire model, but now we need to actually tell PyTorch, hey, when we give this model data, what is going to happen? And that's going to be our forward function, def forward. Do self and then x. X is going to be the input here, okay? So we're going to pass x through all these layers. We're going to do x is equal to self.conv1 x, passing it through the first convolutional layer, x is equal to self.conv2, passing through the second one, and then x is equal to self.fc1x. Beautiful. So it passed through all the layers, and now we're going to return x. And then this should be a number, but should be between 0 and 1. It might not, but once it's done training, it should, be like that, okay? So, our entire structure is done, except for one thing. We don't know what FC input is. And what we can do is trial and error. We're going to pass an image through this model, and then what the error returns, in that area, it's actually gonna show us what FC input should actually be. Let me show you guys. So here I have train, that, let's call this image. We have this image, not train, always name my things train, but it's actually data set. Non-train data set. Great. So we type in the image.shape, and now what we're gonna do is I'm actually gonna unsqueeze this on the first dim, because I'm not gonna go too deep in this, but convolutional neural networks, they like batch data, so we're gonna pretend that this thing isn't a batch. Just do that. Okay, now we can actually create our model. We'll do model is equal to net, no errors, so just make sure everything's ran good. All right, we have a model is equal to net. We'll do model, and we'll pass our image through it. And as you can see, mat1 and mat2 shapes cannot be multiplied. 1 by 1, that 1, 1, 2, 3, 6, and 1 by 5, 12. And we need to make sure that these two inner numbers match, okay? So we're gonna set, one right here is actually our FC input. So we're gonna replace FC input with this big number over here, 11,236. Let's go ahead and try that out. Run that. Beautiful. Now we get a singular output. Now I know it's not between 0 and 1. When this model is actually fine-tuned and trained, it'll of course return a number between 0 and 1. So as you can see, we finally created a model that is able to take in these images and just spit out a number. Now of course, if you train this model on accuracy, it'd be terrible. You know why? Because it's not trained. All these parameters that it has are random. If I do model.stateDict, these parameters that the model uses are all completely random and initialized by pure randomness. So it's not trained at all. It's not going to be good. But in the next episode, we're actually going to utilize our GPU, which we haven't used a lot. And we're actually going to start to train our model, and we're going to be able to produce a model that is able to make accurate predictions on pneumonia X-ray images. I hope you enjoy this one. I'll see you in the next one. Goodbye.